Hello, hello. Thank you very much for joining me again on Custom Camper Adventures. Unfortunately, I haven't done a great deal in the van over the last week. Between the absolutely awful end of the world weather that we're having, it really is being a drippy January, fair play, and the fact that I've been on call, I haven't really had much opportunity to do much work in the van at all. However, I haven't been resting on my laurels. I have been looking at a lot of electrical information online, as I am coming up to the stage where I'm due to do my electrics. And I have to be honest, there's a lot of bad information out there. I've been looking at a lot of online communities, and people have been either giving bad advice or doing bad things. For example, there was one fella who didn't really want to invest in the toolage that you need to do the big crimps. So he sent off to some online companies and ordered his cables prefabricated, which is fair enough. If you don't want to buy a crimping tool the size of a set of bolt cutters, I don't blame you. But that being said, this guy, he ordered a cable for his battery-to-battery charger and his inverter. So he has a 50 amp battery-to-battery charger, and he ordered 10mm cable for that. Not good. He also ordered 16mm cable for a 2000 watt Renogy inverter. And both of them are way too small. And the irony is, after people pointed it out, he actually gave backlash to it, saying, oh, it's fine. But no, it's not. You see, a lot of people think 12 volts isn't dangerous because you can touch it with your bare skin and it won't be a problem. It won't electrocute you, you won't get a buzz, unless you use your tongue or something like that, but I really wouldn't recommend it. You see, the thing is with current, at 240 volts out your wall, you will never draw more than 13 amps or about 3000 watts, which is fine. You got 240 volts to push it through the cable. So yeah, The thing with 12 volt is, because, like I said, you can touch it, it won't harm you. It's, people touch it with a bare skin. It's not a problem. It's not, the 12 volts is not enough to push it through your skin. But to make up for the low voltage, the amount of ampage it has to carry is quite extreme. I mean, you can pull up to 300 amps on a 12 volt circuit. And the problem with ampage is if you don't have perfect connections or any loose connections or anything undersized, that ampage will literally fry the cable. And that's how you get fires. And that's how vans burn to the ground, basically. So anyway, I've put together a little presentation to basically educate on how to do your calculations for like fuse and cable sizing and stuff like that, and pointing out a few safety tips. Again, I will say I am not an electrician. I happen to work with electricity, and my hobbies tend to involve working with low voltage electricity as well. So do not take what I say as gospel. It's just a guide to push you in the right direction. So I accept no liability for any electrocutions, fires, death, or destruction, or any other horrible things that may go wrong while you're doing this. I'm just hoping to hopefully prevent that. So yeah, let's get on with it. This little gem is called the power triangle, and is a part of what is known as Watt's law. And this will be the backbone of everything we're doing today. First of all, you've got your power in watts. You've got your current in amps, and your voltage in volts. If you know any two values on the power triangle, you can easily work out the third. In the context of our explanation, we will take the voltage as 12 volt, as most leisure batteries and electrical systems fall into this value. And I know you're all asking, but Ian, how does it work? Well, I'm glad you asked. Now imagine you're writing down a simple division sum on paper. How would you write it? 100 divided by 5 or over 5 equals 20. This transfers to the power triangle to calculate either of the lower two values, either the amps or the voltage. As you can see, you can either have P, the power in watts, divided by I, the current in amps, to find out the voltage, or the power in watts divided by the voltage to find the amps. For our first example, I thought I'd stick with the easy numbers. If you've got a power of 100 watts and you divide it by 5 amps, you will find that the answer is 20 volts. Likewise, if you take a power of 100 watts and divide it by 20 volts, you will find the current required to deliver that load is 5 amps. Simples, right? The power triangle and these calculations will work universally on AC or DC and any voltage, be it 12 volt or a 24 volt system or a 48 volt system or anything really. But for the purposes of our needs, from now on we will always assume 12 volts, as that's what I'm building, and that's what most people in the campervan world tend to run their systems on. To give you a more practical real-world example, in fact a question I think is asked a lot, let's look at inverters. If you have a 1000 watt inverter, how many amps does it draw? If you take 1000 watts and divide it by 12 volts, so that's P over V, that will give you an answer of 83.33 amps. Now in real life, that number will be slightly higher due to the inefficiencies of the inverter. It tends to be closer to 100 amps, but that gives you a rough guide that you can use to check your cable sizing and your fuse rating. Although in the case of an inverter this will be listed in the MIs, you can see how this can be used to calculate loads on other appliances. Although this next part will be less important to you if you're installing a brand new system, you can also use the power triangle to calculate wattage of an appliance if you know its amp draw, or to work out the maximum wattage that can be used on a specific cable, bus bar or circuit. This can be quite handy if you're adding to an existing system to ensure that your current infrastructure can support what you're adding. Again, we will assume 12 volts. Again, going back to the basic sum principle, I and V are next to each other on the triangle, so you basically stick a multiply in between them. This allows you to work out the power in watts. So if we have a 30 amp current draw, I, and we multiply it by 12 volts, V, that gives us a power consumption of 360 watts. Again, the majority of what you will be doing on a new build will be working out your ampage using P over V to calculate cable sizing and fuses, as most of the time you will know the wattage of the appliance from its data plate or manufacturer's instructions. But the other calculations and workings of Watt's law do have a few niche uses. Like I said, if working out if a particular circuit can handle a load, or when altering systems to add new appliances and ensuring that cables, bus bars, etc. are suitable for any planned expansion, as these normally have their ratings in amps. In any case, once you've worked out your ampage draw on every circuit on your planned electrical system, you can then use a readily available sizing chart to work out your cable and fuse size. Just remember, you must always make sure that your fuse rating is lower than your cable rating, because the last thing you want is to have a fault on a circuit and for your cable to burn before your fuse. Double checking everything on a 12 volt system is incredibly important. You tend to find they don't get the respect they deserve because people can touch them and they don't feel anything. But because of the immensely high amounts of amps involved in a 12 volt system, they do generate a ton of heat and can easily cause fires. And let's be honest, none of us want that. Our vans are incredibly flammable. And on a scale of 1 to 5, that would be an absolute 10. It would be absolutely terrible. So here is a rough diagram of the installation that I will be putting into my van. As you may notice, it is light in some details like certain cable sizes, certain fuse sizes, and other details like that. That is intentional. I do not intend this as an instructional video. This is a guide. If you're building your own system, you'll have to work out your own wiring diagram. As such, I cannot be held responsible for anybody who tries to copy this. I will, however, talk you through one or two of what I feel are important design choices I have made in my system. First of all, isolation. I wanted to be able to isolate all my main components in case I ever have to do any work on them out in the field. So I have a DC isolator from my solar panel going to the MPPT controller. I have an isolator coming directly off the fuse off the leisure battery. I also have an isolator coming from the feed from the vehicle battery to the DC to DC charger. This way, if I turn off all three of them, I can ensure that there is absolutely zero power going to any of my internal components. The second design choice I have made is my AC supply. Now, if you look close at my drawing, you will see I have two separate AC outlets. One straight from the consumer unit from the shore power and one from my inverter. Now, why have I done this, you might ask? Well, let me explain. A lot of people seem to misunderstand how inverters work. For example, when the AC comes in on the shore power, it goes to my consumer unit. My consumer unit has a 6 amp and a 10 amp breaker. The 6 amp will go to my AC to DC charger for charging my battery when I'm on a shore hookup. The 10 amp supply will go to a power socket. I have gone with a Renogy 1000 watt inverter, and although this does support pass-through, there is a caveat there. The Renogy inverters don't have a neutral to earth cross bond. So this means that if you get a fault condition, there's no guarantee that your breaker will trip because there's no bonding between the neutral and the earth. Now this is a problem. There are ways around this. People have come up with some fancy relay designs which can link them when the system switches over from shore power to inverter power. But this is quite complicated. I would say a little bit beyond the realms of DIY, and frankly adds another layer of failure. If that relay fails, then you will not be protected and you will not know. So what I have opted to do is have the inverter go to a separate power socket, which will be for double insulated appliances only. So I'll have RCD protection for the body of my van and for myself from the shore power, and the inverter supply will be on a separate supply, which I know I can use relatively safely when I'm out and about. So why is this important? Right, basically it comes down to the differences between how shore power and inverter power work. On shore power, you have live, neutral and earth. On the live, you'll have about 230 volts AC. On the neutral, you'll have close to zero, and on the earth, you should have zero. Under a fault condition, this sends a current back across the earth, the RCD picks up the imbalance, and it trips. From an inverter, you have about 120 volts on the live phase, and about 120 volts on the neutral phase. And the earth doesn't really go anywhere, for lack of a better explanation. So when you get a fault condition in an inverter, your inverter will overload and trip out, but it's much slower than an RCD, which should trip almost instantly, or even an MCB, which will trip quickly in an overload scenario. As such, this is why inverters should only be used with a double insulated appliance, because the earth doesn't really have a real value. This is also the same for all the power stations. Like I have a Jackery 1000, which will also augment my AC supply. This actually applies to them as well. This is one of those things that nobody really pays attention to, and people will even argue against this and say, well, it's alright, it's worked on my van for years. This is a classic case of one of those things that's alright until it isn't. If you get a fault condition on an inverter supply, and say it makes the body of an appliance or the body of your van live, you could touch it when you're grounded to outside, for example, you would get an electric shock, and there's no guarantee that anything will trip. This is something I feel that is very important that people should understand about inverters. They're perfectly safe if used properly and with respect. Anyway, now that we have all the doom and gloom out of the way, I'm showing on screen a list of all my appliances and power draws, what their ampage and wattage is, and basically what sort of cable I need to put them on and fuse. Again, this is just a rough guide, and I will probably make alterations to it, but this is a sort of cornerstone that you need to put together so you can actually do yourself a working diagram. With regards to wire sizing charts, I'm picking the two I have been using on screen now for you to take screenshots of if you so desire. They're also readily available on the web if you just Google them. There are literally dozens of them available, way more than the two I've put up. Now, if you're still here after my 13 minutes or so of waffling, I doff my cap to you. Thank you very much. I do appreciate it. I do hope this information has been useful to you and will aid you in your build of your van. If you have any questions, comments or feedback, please feel free to put them down in the comments below this video. I would gladly get back to you. And now, back to me in my cold, wet and miserable van. So, if you've made it this far, I thank you for watching. Nobody likes being lectured or doing little school lessons or looking at like PowerPoint diagrams, even though I didn't make it in PowerPoint. But I do hope you found this information useful. I hope if you are planning to do your own electrics, it will point you in the right direction and give you a rough idea how to basically do everything. Again, thank you for bearing with me in this one. I know it's something a little bit different. And again, if you found any of my content either useful, informative, entertaining, or even amusing, please feel free to like and subscribe. Thank you very much, and until next time. See, as voltage goes down, ampage goes up, basically. I'm actually getting a call out. All right, Shell.
Hello, mate. All right?
Yeah, not bad. Yeah. I'll tell you what, though. I don't know what it is with you, but whenever you call me, I'm always on the toilet or doing something. Do you know what I'm doing right now?
Taking a shit?
No, I'm actually sitting in my van, right?
Yeah.
I've got my camera on. I've got my microphone in my hand. And I was actually recording the intro to my next video.